Let's look at cone clutches now. A cone clutch can be considered as the general case of a disc clutch having a cone angle of 90 degrees. In a cone clutch, instead of mating two spinning discs, the cone clutch uses two conical surfaces to transmit torque by friction. Due to its increased frictional area and the wedging effect, a cone clutch is able to transfer or convey larger torque when compared to a comparable disc clutch. Now what happens is cone clutches are used for specialist transmission, for example in racing, for instance railing cars, or maybe for extreme off-road vehicles. This is because the clutch does not have to be pushed in all the way and the gear change can be done much quickly. So here we have a typical cone clutch setup. So one indicates the cone, the green one is the female and the blue one is the male, and on the male one we will have our friction surface. 2 is the shaft which is connected to the male cone. 3 is again your friction material. 4 the spring. 5 is the clutch control separating both the cones, and then finally 6 indicates the direction in which it is rotating. So once the clutch is engaged, you will see that instead of disc being in contact, this friction surface is going to be in contact to the surface which is machined onto the female cone, and due to this the frictional area increases, and at the same time it is also able to transfer greater torque because of the wedging action. So now this is just the schematic showing the clutch angle or the cone clutch angle, the outer diameter, the inner diameter. So similar to disc clutch, we've got uniform wear case as well as uniform pressure case for cone clutches, and the equations are respectively similar. The only difference is the actuating torque remains unchanged. So these equations are for uniform wear, and you'll see that equation 11 is same as equation 1. The actuating force remains unchanged, but when we look at the torque calculation, you'll see that in the denominator we have a sine alpha component coming in. So this is for uniform wear and this is for uniform pressure. So the only difference you'll see is that for your torque, you'll see you have a sine alpha component coming in, but apart from that everything else remains the same. Again, we need to be mindful of the fact that we use appropriate equations, for instance for uniform pressure as well as for uniform wear. Now what happens is, if the mean diameter is given, then the torque and the actuating force can be calculated using the formula that is given below, right? And then what happens is your torque is nothing but F, small f is your coefficient of friction, Fa is the actuating force, capital D is the diameter of the cone clutch system, and then the actuating force is given by P max pi BD sine alpha, where B is the width of the friction surface or the cone face. Now let's look at example 4. The contact surface in a cone clutch has an effective diameter of 80 mm. The semi-angle of the cone is 15 degrees. The coefficient of friction is 0.3. You have to find the torque required to produce slipping of the clutch if the axial force applied is given as 200 Newton. So in this case what happens is you have to find the torque. So in this case what happens is the outer diameter is given, the inner diameter is not given. So basically what should happen is we'll use equation 17 I to calculate the torque. So coefficient of friction is given, we know the actuating force, the diameter is given as 80 mm, converting it to meters. So substitute everything into the equation, you'll say that the torque that is required to, or the torque that is transmitted by this cone clutch system is nothing but 9.27 Newton meter. Now just looking at adding on to example 4, the same clutch is employed to connect an electric motor which is running uniformly at a speed of 900 revolutions per minute with a flywheel which is initially stationary. The flywheel has a mass of 14 kg and the radius is 160 mm. So what you need to do this time around is to calculate the time required for the flywheel to attain full speed and to calculate the angular acceleration. So in this case, what we have is we have to consider the moment of inertia of the clutch system. So again, the torque that is transmitted is from the previous part of this question. So the first thing that we need to do is we need to calculate the moment of inertia I. So for a solid disc, it is simply given as half mr squared. The radius was given, the mass was given as 14 kg. So we have calculated that the moment of inertia is nothing but 0.1792 kg meter squared. Now on the other hand, we know that your torque, now what we're doing is we're not looking at we're looking at rotational motion. So in this case, when we look at maybe linear motion, so your force is mass times acceleration, but in rotational terms everything changes. So your force becomes your torque, your mass becomes your inertia, and your acceleration becomes your angular acceleration alpha. So what we do is we can calculate our alpha, which is our angular acceleration. Torque we had calculated earlier, so your moment of inertia is here. So we get our angular acceleration is 51.73 rads squared, right? Now what we do is, again, this expression is your kinematic equations. So instead of linear, we're converting everything into angular. So your final velocity, your angular velocity, is equals to your initial angular velocity plus your angular acceleration times the time. So we know that our final angular velocity is simply given by 2 pi n upon 60. So the cone clutch was rotating at a speed of 900 revolutions per minute. So converting that to rads per second, we get 94.25 rads. Now what happens is the initial velocity is 0. So the initial angular velocity is 0 because the question says that the cone clutch is started from rest. So omega I is 0. So we can simply solve for t. So what we get is it takes the cone clutch to reach a speed of 900 revolutions per minute in just 1.82 seconds. The last part of this chapter is looking at centrifugal clutch. So a centrifugal clutch is a clutch that uses centrifugal force to connect two concentric shafts with the driving shaft nested inside the driven shaft. So this schematic shows the centrifugal clutch is contained inside the driven shaft. So this, the outer one is your driven, and this, the inner one, is your driving. So what generally happens is, as the driving shaft rotates, the clutches are suspended with the help of springs. So as the centrifugal force increases, the shoe that you see, or basically the clutch that you see, will move outwards, and once that happens, it will stick or press onto this driven shaft, and it will cause the driven shaft to rotate as well. And this kind of setup is generally seen in a brush cutter. And these are all examples of centrifugal clutches. You'll see that the shoe contains the clutch plate, and what generally happens is, as the speed of the driving shaft increases, the centrifugal force also increases, and as a result of this, the shoe moves outwards. Once this happens, once it eventually comes in contact with the driven shaft, the driven shaft starts to rotate at the same speed at which the driving shaft is rotating. So once more, what generally happens is, in the beginning, when the driving shaft is not rotating, the shoe is suspended by the help of the spring, and there is no direct contact between the clutch or the shoe here onto the driven shaft. As the speed increases, the shoe starts to move outwards due to the centrifugal force acting, and eventually the shoe presses and sticks onto the driven shaft, and the driven shaft starts to rotate as well. So now what happens is, just looking at the operating principle of a centrifugal clutch, the shoe moves radially in guides and are held against a spider on the driving shaft by means of springs, as shown before. The springs exert a radial inward force. The weight of the shoe when rotating causes radial outward acting force, which is your centrifugal force. When the centrifugal force is less than the spring force, the shoes remain in the same position. So basically what happens is still there is no contact between the shoe and the driven shaft. When the centrifugal force exceeds the spring force, the shoe moves outwards and comes into contact with the driven member of the driven shaft and presses against it. The force with which the shoe presses against the driven member is the difference between the centrifugal force and the spring force. The increase of speed causes the shoe to press harder and it enables more torque to be transmitted. So now let's look at the analysis of a centrifugal clutch. M is the mass of the shoe, N is the number of shoes, R is the distance of the center of gravity, omega is the angular speed, mu is the coefficient of friction, L is the contact length of the shoe, B is the width of the shoe, theta is the subtended angle or the angle subtended by the shoe, which should be given in radians, and P is the intensity of pressure. So your centrifugal force Fc is simply given by equation 18, which is m omega squared r, and r is nothing but the distance of center of gravity, and capital R is the inside radius of the pulley rim. So you should be mindful of these two, right? So small r is the distance of the center of gravity and capital R is the inside radius of the pulley of the rim. So now what we have here is the centrifugal force is given by m omega squared r. R is the center of radius to the gravity. Spring force Fs is simply given by 9/16 m omega squared r, and then the net outward radial force is nothing but the difference between your centrifugal force and your spring force. So equation 18 minus equation 19, you end up with a net force of 7/16 m omega squared r. So that's your net outward radial force. The frictional force F is simply given by mu times your net force, and the torque is nothing but torque is given by F times your capital R, which is nothing but mu F net R, and this capital R is the distance from the center to the radius of the rim. And then you can use equation 23 to find the contact length, the width and the shoe, and these are related by using equation 23. So now let's look at example 5. A centrifugal clutch is to be designed to transmit 15 kilowatt of power, and the clutch is rotating at a speed of 900 revolutions per minute. There are 4 shoes with subtended angle of 60 degrees. The inside radius of the pulley rim is given as 150 mm. The distance from the center of gravity is 120 mm. The coefficient of friction is given as 0.25. The pressure is given as 100 kilopascal. So determine the mass of the shoe. So your power is simply given by tau omega. So your braking torque times the angular velocity. So power was given as 15 kilowatt. So we can find our angular velocity by using 2 pi upon 60. So your angular velocity was 94.25 reds. So your torque is simply 159.15 Newton meter. And we know that your F net is simply the difference between your centrifugal force minus the spring force, and which is nothing but 7/16 m omega squared r. So 7/16, we don't know the mass of the system, so just use m. Angular velocity was given as 94.25, so squared, and then r is the distance to the center of gravity, which was given as 0.12. So we end up with the F net value of 466.36 m, indicating that we don't know the value of mass Newton. So that's done. And we know that the torque is simply given by torque is equals to Fr, which is simply